Today we are on Lesson 6 of Unit 13, pages 469 to 471. Practice with sampling distributions, and you want to have a calculator available just for adding, subtracting, and dividing purposes. And your homework is pages 472 to 473. So exercise number 1 on page 469. Red Lobster is interested in determining the average tip at their restaurants. They took a random sample of 157 tips from their restaurant. Based on the data, they ran a simulation for 1,000 total samples. So the sample size is 157. And it was simulated 1,000 times. So that means there are 1,000 dots here. The results are in the table below. A, using the dot plot only, estimate the confidence interval. Okay, so to estimate a confidence interval, what we do is we cut off 2.5% of 1,000 from each tail. So 0.025 times 1,000 is 25. So we cut off 25 dots in each tail. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 25. And from the right tail, okay, so if this is 3.40, this would be 41, 42, 43, 44, 45, 46, 47, 40, 48. So this is 3.48. And if this is 4.2, this would be 21, 22, 23, 24. So 4.24. Okay, so our confidence interval is 3.48 to 4.24. This is our 95% confidence interval to the nearest hundredth. And just, I mean, look at this. This is so about 95, I could actually say the actual number, 950 dots would be from here to here. All in here encompasses 950 dots. Use the confidence interval to estimate the mean and margin of error. Okay, so the mean is going to be the sum divided by 2. 3.48 plus 4.24 divided by 2. Punch that in the calculator. And we get 3.86. The margin of error. Once you have your confidence interval and now you have your mean, you can simply take B minus your mean. That will give you the margin of error. Or you can always fall back on and use it is B minus A divided by 2. In this case, it would be 4.24 minus 3.48 divided by 2 into the calculator. .38. And let's not forget to add the plus or minus. Your margin of error is always plus or minus. Do you think it is reasonable to conclude that the actual mean of Red Lobster tips, population mean, is $3.60? Explain your answer. Well, our question is $3.60 in our confidence interval? It is. So yes, $3.60 is within our confidence interval. So it is within our 95% confidence interval of $3.48 to $4.24. And just $3.60 would be here. Right? Which again, looking at this, it lies within our 95%. D, is it reasonable to conclude that the population mean tip of all Red Lobster's tips is $4.50? Well, no, it's not within our confidence interval. Right. We say $4.50 is outside our confidence interval. So it is unusual. And you see in our simulation above, $4.50 didn't even occur, right? It would be way out here. The actual mean of the sampling distribution of sample means is $3.85 with a standard deviation of 20 cents. Find the margin of error. Okay, well, the margin of error is easy. The margin of error is just going to be twice the standard deviation. So 2 times 0.20 is 40. So 0.40, sorry. So our margin of error is plus or minus 0.40. And then our confidence interval would be our mean plus or minus our margin of error. So 3.85 plus or minus 0.40. Subtract that, it'll give me 345. And adding that would be 425. So this is our confidence interval, and this is our margin of error. How close was the actual confidence interval to the one we estimated from our DAT plot? Well, it's very close. This is $3.45 to $4.25, and this was $3.48 to $4.25. So it was very close. Only pennies off. Exercise number 2. As of December 30th, 2018, the Brooklyn Nets record was 15 wins and 18 losses. What proportion of the games had the Nets won at this point in the season to the nearest hundredth? Okay, well, they're played 33 games to that point, and they won 15 out of the 33. And to the nearest hundredth, 15 divided by 33. It's 0.45 repeating, so 0.45 to the nearest hundredth. Before the season started, your friend who is a Nets fan stated that the Nets had on average, a 65% chance of winning each game this season. To test this theory against the Nets' current record, you run a simulation based on the assumption that the Nets have a 0.65 chance of winning games. Each dot in the plot below represents proportions of games the Nets win. Each of sample size 33, simulated 100 times. So there's 100 dots here. The mean proportion of simulated sample distribution is 0.658, and the standard deviation is given to be 0.093. Use the information to determine the 95% confidence interval. Okay, so we know that is simply the mean plus or minus 2 times the standard deviation. 0.658 plus or minus 2 times 0.093. Throw it in the calculator. Excuse me, 0.844. And go up, grab that, change the plus to a minus, 0.472. This is our confidence interval. Using your answer to part A and the confidence interval in part B, does the Nets' current record support the claim that they have a 65% chance of winning each game this season? Well, no, because this 0.45 is an unusual value. It does not lie. It is outside our confidence interval. .45 is an unusual value. It is outside the 95% confidence interval. Why was it appropriate to use a sample size of 33 for this simulation? The Nets had played 33 games so far in the season. Because you do not want to seem overly argumentative, you propose to your friend that the Nets could have a 55% chance of winning each game this season and provide the following simulation data to support your claim with a proportion of 0.55 and a sample size of 33 simulated 100 times. So there's 100 dots here. In the following 2 ways, explain to your friend why the simulated dot plot supports your claim even though the sample proportion of 0.45 from the beginning of the season is in the left tail of the dot plot. Let's see, our 0.45 is here. Well, informal, 0.45 is not an extreme value. It would be right here. It occurred several times. 0.45 is not and extreme value. In this dot plot. The formal explanation, well, does 0.45 lie within the confidence interval? So if we're given the mean proportion is 0.554 and the standard deviation, let's find the confidence interval is going to be the mean plus or minus 2 times the standard deviation. So 0.554 plus or minus 2 times 0.094. Throw that into the calculator. .742. .366. .45 is in the 95% confidence interval. Exercise number 3, a candidate for a political office commissioned a poll. His staff received responses from 900 likely voters, and 55% of them said they would vote for the candidate. The staff then conducted a simulation of 1,000 more polls of 900 voters, assuming that 55% of the voters would vote for the candidate. The output of the simulation is shown in the diagram. Given this output and assuming a 95% confidence interval, the margin of error for the poll is closest to, okay, so we actually have like a bar graph here, and for a 95% confidence interval, the margin of error, well, we have 4 choices here. So in this case, we actually want to look at our choices. Our 0.55 plus or minus the margin of error would encompass 95% of this data here. So 0.55, our mean, plus or minus the margin of error. So if I took 0.55 plus or minus 0.01, that's going to get us from 0.54 to 0.56. So 0.54 would be about here to 0.56 would be about here. Does that encompass 95%? No. This is too small. .03 would be 0.52 to 0.58. So 0.5, this is probably likely, all right? From here to here, does this look like we have about 95% of the data values in this range? This is likely. And let's just try this one. 0.55 plus or minus 0.06. That'll bring us to 0.49 to 0.61. That encompasses all of them. That's 100%. So this is too large. This is too large. And then this is even greater. So it is choice 2. Exercise number 4, Anne has a coin. She does not know if it is a fair coin. She flipped a coin 100 times and obtained 73 heads and 27 tails. So her proportion of heads was 73 out of 100, or 0.73. She ran a computer simulation of 200 samples of 100 fair coin flips. So there are 200 dots here. And each represents the proportion of heads out of a sample size of 100. The output of the proportion of heads is shown below. Given the results of her coin flips and of her computer simulation, which statement is most accurate? Okay, so for her coin flip, her proportion of heads was 0.73. Now with the simulation for a fair coin flip, we have a mean and standard deviation given to us, so let's calculate the confidence interval. Our confidence interval is the mean plus or minus 2 times the standard deviation. So a mean of 0.497 plus or minus 2 times 0.050 is 0.397 to 0.597. So we are 95% confident that a fair coin flip would have a proportion of heads in this interval. Given the results of coin flips of her computer simulation, which statement is most accurate? 73 of the computer's next 100 coin flips would be heads. Definitely not. That is way outside our confidence interval, and there's no way we can actually state that, oh, the next 73 out of 100 coin flips would be heads. 50 of her next 100 coin flips will be heads. No way we could state that either. Her coin is not fair. Again, we would expect the proportion of heads for a fair coin to be, we're 95% confident it would be anywhere between 3.97 to 0.597. So her 0.73 is outside the interval, so her coin is not fair. 0.73 is not within the fair coin confidence interval. So it is choice 3. Now the homework, pages 472 and 473. 472 is similar to the notes. 473, you need a calculator to calculate the mean and standard deviation. So question number, this must be number 3. Yeah, question number 3. You've got 8 out of 40, and the first paragraph is 0.2. And then the dot plot. Again, if you have the calculator, please enter the information in. Stat edit, completing both list 1 with the proportion values and then list 2 with the frequency. But if you don't have a calculator, then there are the answers to number 2. The mean rounding to nearest hundredth is 0.30 and the standard deviation to 0.07. But then you can answer the remaining 3 questions on that page. All right. Thank you once again for your attention, and have a good day.